Hey everyone, welcome to our fifth unit in Calculus AB. Fifth unit, we're going to start talking more about analytical applications of differentiation. Okay, and then a major one that we're going to start off with today is called the mean value theorems. That's our topic 5.1 for today, using the mean value theorem. All right, before we introduce the main topic of the section, the mean value theorem, let's start with a very special case of this theorem called the Rolle's theorem. All right, so Rolle's theorem, if we place 2 points anywhere on this coordinate point, they have the same y value. So how about 1, 2 and 4, 2, right? They both have the same y value. I mean, connect those 2 points with any continuous function. It has to be a function, it has to be continuous. So maybe it looks like that, right? Rolle's theorem says that there must be at least one point on our function where we could draw in a tangent line that is horizontal, or that the slope is 0. Let's take a look at our function here. And in fact, your crazy teacher here drew much more than one. There's one here, 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 and here. Okay, the fact that there's 4 doesn't mean anything special. Rolle's theorem simply says that there has to be at least one. Okay? Now we see 4, but we could have easily drawn one that was 1 or 2 or 3 or 100. Well, that wouldn't have been that easy, I guess, but it is possible to draw one where there's hundreds of points where the tangent line is horizontal. All right, and this activity models an important concept called Rolle's theorem. All right, so Rolle's theorem. Rolle's theorem says that if 3 things are true, what 3 things are we looking for here? 1, the function is continuous on a to b, the function is differentiable on the open interval a to b, and the 2 endpoints have the same y value. Then there is at least one time on that open interval that the derivative equals 0, that the slope equals 0. All right, so let's take a look at what that looks like here. You'll need a graphing calculator to confirm some of the items that we talk about in this section today. So number 1 says determine if Rolle's theorem applies to f of x equals x to the 4th minus 2x squared, any interval -2 to 2. State thoroughly the reasons why or why not the theorem applies. If the theorem does apply, find the value of c guaranteed by the theorem. Confirm your result by graphing the function in the coordinate plane to the right. All right. So we need to see if 3 things are true in order for Rolle's theorem to apply. And the first thing is this function has to be continuous on this interval. All right, so f of x, is it continuous or not? Well, think about what this function would be. Think about, are there any holes in that function, any jumps in that function, any vertical asymptotes in that function? It's just your standard quartic function. So there are not going to be any holes, jumps, asymptotes, vertical asymptotes in that function anywhere, but specifically on this interval, -2 to 2. So f of x is continuous on the closed interval, -2 to 2. That's the first of 3 things that we have to make sure is true. The next thing that has to be true is that the derivative is also continuous. In other words, the original function is continuous. So if we take our derivative, we have 4x cubed minus 4x. All right, there's not going to be any holes, jumps, or asymptotes in that function either, which means the derivative is continuous, which means our function is differentiable. Okay, remember the way that we remember from back in chapter 2, remember differentiables on the open interval. We don't care about differentiable at -2 or 2 here, just the open interval. We talked about differentiability. There's many different reasons why a function could not be differentiable. It might not be continuous, but we already saw that it was continuous, so that's good. It might have a cusp in it. Okay, it might have a sharp turn in it. It might have a vertical tangent line in it. Okay, but by taking the derivative and making sure that's continuous, we are getting rid of all those possibilities. So it's continuous on the closed interval. It's differentiable on the open interval. So the first 2 things are true. The last thing we got to check is, are the 2 ending y values the same? Does f of 2 equal f of -2? All right. If you put 2 into our function, we would get 4, 8, 16 minus 2 times 4, which is 8. So that would be 8. If we put negative 2 in, we'll get the same answer back. So since f of negative 2 equals f of 2, the third thing that we need to check for Rolle's theorem to apply is true. All three of these items are true. Therefore, we can say Rolle's theorem applies. And I can tell you, making sure that it applies is much more difficult than actually using the theorem. Okay? We'll have more work in just making sure that it applies here. Because once it applies, what do we mean by it applies? That means at some point, the derivative is 0 on the interval. So all we're going to do is take our derivative that we've already found and set that equal to 0, and then solve. All right, so if we solve this, if we factor out a GCF of 4x, what's left is x squared minus 1. And if we factor that, 4x times x plus 1, x minus 1, we get three answers of x equals 0, negative 1, and 1. Okay? So those might all three be the answers, or there might only be one answer. Or, of course, two of them might be the answer. How do we know which are or not the answers? We're looking at this interval right here. Any of these numbers that are included in this interval are our, quote, C values. Okay? If they're not in that interval, then they don't mean anything for this problem. But since all those are on our interval, all three of those are our C values. So that means on this graph, negative 1, 0, and 1, at x equals those three numbers, there'll be a horizontal tangent line to our function. Okay, so if you wanted to right now, take out your graphing calculator and graph this function in y1 between negative 2 to 2. And if we graph this properly, it should look something like that. And you can see there are definitely 3 points here, here, and here. The graph has a horizontal tangent line, the 3 x values that we originally set. But that's not the main topic today. The main topic is called the mean value theorem. Rolle's theorem is a special case of the mean value theorem, which says if f is continuous in the closed interval a to b and differentiable in the open interval a to b, which is the same as Rolle's theorem, but you'll see there's no special third part here. We don't need to check if f of a and f of b are the same. There exists a number c in a to b such that the instantaneous rate of change at c will equal the average rate of change over the interval. Remember, this is just a slope at a point, slope of a tangent line. This is the slope between 2 points, slope of the secant line. So mean value theorem is simply saying that the slope of a tangent line will equal the slope of the secant line at some point on that interval. Again, it could happen twice or 3 times or 100 times. But usually we just try to find 1, maybe 2. So what does the mean value theorem look like? Let's take a look at a graph of that. In the figure to the right, let's label the indicated order pairs. All right, so this one right here is a comma f of a. This one right here is b comma f of b. Okay. Label a segment whose length is f of b minus f of a. So if we draw in a segment whose length is fb minus f of a, that would be the difference in y's. So this right here is f of b minus f of a. And then it says to label a segment whose length is b minus a. That's just your change in x's. So the length of that one, that blue line there, is b minus a. The quotient f of b minus f of a over b minus a is simply the slope of the segment joining the points a f of a and b f of b. Draw in this segment. All right, so we'll simply draw in this segment here that goes between these 2 points. And the slope of that line, rise over run, is f of b minus f of a over b minus a. F prime of c gives the slope of the line tangent to the curve, or the tangent line to the curve of f of x at the point c comma f of c, which we don't see up there on our picture right now. On the graph, locate the c value that is guaranteed by the mean value theorem and draw a line tangent to the curve at x equals c. In other words, we're trying to find a line that is tangent to that black curve right here, but parallel to this green line. Okay, and that's going to be probably somewhere around there. All right, it's not a perfect parallel line, but it's pretty close. And that point right there is c comma f of c. On the graph above, locate the c value that's guaranteed by the mean value theorem. That's what we just did. We drew a line that's tangent at that point as well. The 2 lines drawn on the graph of f of x, we've already said this, are parallel to each other. The green line and the purple line in my picture there are parallel to each other. The conclusion of the mean value theorem can be restated as follows. There will be 2 parallel lines, one through a f of a and b f of b, and the other tangent to the curve at c f of c. Just another way of thinking about what the mean value theorem says. A secant line going through 2 points and a tangent line passing through 1 point that are parallel. So let's take a look at another one here. Determine that the mean value theorem applies to f of x on the interval 1 to 5. State the reasons why it does or does not. If it does apply, find the value of c guaranteed by the theorem. Visually, what is the mean value theorem trying to find? Let's draw that in as well. All right. So the first thing we got to make sure is that this function is continuous. Here, let's just copy down our function here. On the interval 1 to 5. This function is actually not continuous. Where is it not continuous at? It's not continuous at x equals 0. Okay, there would be a vertical asymptote in the graph at x equals 0. But lucky us, x equals 0 is not on our interval. So this function is continuous on 1 to 5. And that's why we mentioned the interval, because if we just say it's continuous, that's wrong. That's a lie. It is not continuous, but it's continuous on that interval. Okay. Next we got to figure out, is the derivative continuous? So let's take our derivative. The derivative of 3 is 0. The derivative of negative 5 over x, remember that's negative 5x to the negative first. So it would be 5x to the negative second, or 5 over x squared, which again is not continuous at 0. But at 0 is not on our interval. So therefore, our original function is differentiable on the open interval 1 to 5. And that's all we need for a mean value theorem to apply. Okay, we do not need to check any other values. So we're good there. We can stop there and say mean value theorem applies. All right, so to actually do the mean value theorem, all we're going to do is the slope of the secant line, so f of 5 minus f of 1 over 5 minus 1 equals the slope of the tangent line, f prime of x. Okay, so again, slope of the secant line equals slope of the tangent. Average rate of change equals instantaneous rate of change. So f of 5, if we put 5 in, we get 3 minus 1, which is 2. If we put 1 in, we get 3 minus 5, which is negative 2, over 5 minus 1. Our derivative we already found was 5 over x squared. So that gives us 4 over 4 equals 5 over x squared, or 1 equals 5 over x squared, or x squared equals 5. So x equals plus or minus square root of 5. All right. Do we have 1 or 2 answers? Right now we got 2, but look at our interval. It's 1 to 5. So the root 5 is the correct answer, however, but the negative root 5 is not. So C equals root 5 is our only answer on this interval. Okay? So root 5, a little bit bigger than 2, probably like, I don't know, 2.2-ish. Okay? If we drew in our secant line, here's the secant line between 1 and 5, and we drew in the tangent line around root 5. Let's try that again. There we go. Those two should be parallel. Example 3, another mean value theorem problem. Find the equation of the tangent line to the graph on the interval 0 to pi at the point which is the solution to the mean value theorem. Okay, so first of all, is that function continuous? Well, let's think about that graph. There's no holes, no jumps, no asymptotes in the graph. It's continuous everywhere. So it's definitely continuous. On 0 to pi. Take our derivative. F prime of x equals 2 plus cosine, which is also continuous everywhere. So therefore, our function is differentiable everywhere, but more specifically, differentiable on the open interval 0 to pi. And because of all this stuff is true, mean value theorem must apply. Okay, so now we can do our slope of the secant line. Equals the slope of the tangent line. F of pi, so if we put pi in here, we would get 2 pi plus 0 plus 1, or 2 pi plus 1. If we put f of 0 in here, so 0 in for x, we would get 0 plus 1, so 1, over pi minus 0, equals 2 plus cosine x. And then we just solve this equation here. So we end up with 2 pi over pi equals 2 plus cosine x, 2 equals 2 plus cosine x, 0 equals cosine x. So obviously this occurs at infinitely many answers, but we're looking at the answer that's on 0 to pi. That only happens once. All right, that would be when x is equal to pi over 2. So our c value here is pi over 2. All right, that's not the final part of this question. It's asking for more than this. It's asking for the equation of the tangent line at that point. All right, well, that's no problem. All we do now is find a point and a slope. We have our x-coordinate at pi over 2, so we want to find f of pi over 2 and f prime of pi over 2. All right, so f of pi over 2 would be 2 times pi over 2, which is pi, plus sine of pi over 2, which is 1, plus 1, so pi plus 2. F prime of pi over 2 would be 2 plus cosine of pi over 2, which is 0, or 2. So our final answer for our tangent line here would be y minus pi plus 2 equals 2 times x minus pi over 2. And we could do a whole lot of simplifying with that if you want, but this is a good enough answer for us here. You know, if you really want to get a simplified answer here, we get there, and then we can add pi's to both sides, add 2 to both sides, and we would get 2x plus 2. Okay, but this answer is fine. It's point-slope form. Slope-intercept form. Example 4, I'm just going to look at a couple where the mean value does not apply and why they don't apply here. So for this one, this is continuous everywhere. No problem, it's continuous everywhere. But thinking back to chapter 2, we know absolute values are not differentiable everywhere. They're not differentiable at the sharp turn. The sharp turn here happens at x equals 3. So we would know that f of x is not differentiable at x equals 3. So we would say, therefore, MVT does not apply. Okay? Part B, we don't even have to get to differentiability because this one is not continuous at -2. And -2 is on our interval. So, a couple small changes here. We would say it's not continuous at x equals -2, and therefore the mean value theorem does not apply. Okay, and the last one here, x to the 2/3, that's continuous everywhere, so that's no problem. But if we take our derivative here, we get 2/3 x to the -1/3, or 2 over 3x to the 1/3. So the derivative is not continuous at 0, which means the original function is not differentiable at 0. And therefore the mean value theorem does not apply. Which brings us to our last problem here. Real world application of the mean value theorem. All right, 2 stationary police cars equipped with radar are 5 miles apart in a highway as seen in the figure. As the semi-truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck did or did not exceed the 55 mile per hour speed limit at some time between the 2 police cars. All right, well, to do this, we know that its instantaneous velocity at these 2 checkpoints did not surpass the speed limit. But let's see if the average velocity did. So to find average velocity, all we're going to do is distance over time, right? So its distance is 5 miles. Let's do it this way here. Velocity equals 5 miles over 4 minutes. Converting that to miles per hour, 60 minutes over 1 hour, we would get 5 times basically 15, which is 75 miles per hour. All right, well, that's probably not good for the trucker. His average velocity was 75 miles per hour. So his instantaneous velocity here was 55, his instantaneous velocity here was 50, but his average velocity between here must have been 75 miles per hour. So think about it this way. Is the truck's path continuous on a highway? right? There's not going to be any, he's not going to magically jump his car from one place to another, right? There's no holes that he's going to be somehow going through and finding himself on the other side. So this is a continuous path, okay? Also, this is a differentiable function because the trucker can always just glance down and determine his speed by looking at his speedometer as well. So the average velocity is 75, which means at some point by MVT, right, this trucker, his instantaneous velocity must have been at least 75 miles per hour, okay? That means he was speeding, and the police officers do have the right to issue him a speeding ticket. That'll do it for our look into the mean value theorem. All right, I hope you enjoyed today's lesson, and looking forward to teaching all of you the rest of Unit 5.